Hi, welcome to my channel, JaberTime, where I do math videos from algebra to calculus and differential equations, simplified with examples. Sometimes I add more videos about apps and programs to enhance teaching and learning online. If you're new here and you liked this video, hit the like button and subscribe. If you have any comments or questions, leave them down below. And I want to thank you for watching and hope to see you again and again. Thank you. Derivatives as rates of change. Calculus as the mathematics of change. Pretty much everything in life changes as we go. I don't want to make the story too long, but calculus is all about rate of change and life is about rate of change. Calculus 4 is differential equations, which is when you have 2-3 items, they change and they depend on each other. So it's more advanced than just like x and y. Here we're gonna just focus most of the time as x and y prime. Okay. To stick to the topic and stay with it, I have probably it's gonna be close to 40 minutes recording. So if you see like I'm going a little bit fast, I have everything written. And I want to make myself, force myself not to make it over 41 or 45 minutes. Here we go. One-dimensional motion. A car moving along a straight street. That's called horizontal change or move. A projectile launched into the air. That's called vertical. Position and velocity. Suppose an object moves along a straight line and its location at time t is given by the position function s equals f of t. All positions are measured relative to a reference point s equals 0. So if you start at location 5 on the number line and you move to, let's say, number 7, we move to units. That's called displacement. But we prefer to have the position instead of at 5 at 0. So we kind of like count from 0, not from 5. That's the reference point. As you can see, I have all the notes clear for you. That's why I'm trying to read a little bit fast and cover enough examples. The displacement of the object between t equals a and t equals a plus delta t is called delta s, which is f of a plus delta t minus f of a. That's like delta y in algebra, where the elapsed time is delta t. Here's another view of what is going on. This is my start point. That's my reference point. Down the road at a, or when t equals a, I have the location or the position s of a. S equals f of a. After some time change, we have s equals f of a plus delta t. So we're moving from this at a to a plus delta t to another location. This much is called displacement, and it's called delta s, which is f of a plus delta t minus f of a. Let me explain more with a graph that we have seen similar ones before in previous videos. This is our function in black. That's s of t. This green line is the secant. This blue line is the tangent. We are going from t equals a to another t or time that is a plus some difference in time, delta t. This has an output which is called f of a. This has an output which is called f of a plus delta t. The difference right here is called displacement, which is delta s equals f of a plus delta t minus f of a. This delta t is like delta x for us. Rise over run. That is the slope. What's the slope of the green line of the secant? It's just like delta S over delta T. But we care more about the blue line. The tangent line gives instantaneous velocity. Let me give you a quick example, then I'll get back to the topic. If you're going from 5 p.m. to 7 p.m. driving, and you cover 150 miles, then you might say differently that I covered 150 miles and it took me 2 hours. So you could say on average, you drove like 75 miles per hour, which is true. That's why we call it on average. So the average velocity is the speed or somehow the change of rate between two distinct points. That's this one and this one. And if I ask you differently, what was your velocity or speed at 5:15 p.m. at that exact moment? Well, that's called instantaneous. And that's why we need a tangent. And that happens when you apply the limit. The limit as delta t goes to 0. All right? We've talked about this before, but I just want to let you know. This is called velocity. So the first derivative in our topic for today's lecture is actually velocity. Instantaneous velocity. All right. Let's talk about some keywords and stick to the topic. Velocity, speed, and acceleration. The velocity will be the first derivative. The speed will be the velocity but absolute value because speed is always positive. Acceleration will be the second derivative. Suppose an object moves along a line with the position s equals f of t, then the velocity is the first derivative of s of t. The speed is the absolute value of the velocity. It's always positive. The acceleration is the second degree of s of t or the derivative of the velocity. So you start at s, you find derivative, that's called v. You find the derivative again, that's called acceleration. I don't want to keep reading this. It's already written with colors and highlights. Let's move on and see how could we talk about this with numbers and examples. Position, velocity, and acceleration. Suppose the position of an object moving horizontally along a line after t seconds is given by the following function s equals f of t, where s is measured in feet with s is greater than 0 corresponding to positions right of the origin. We kind of talked about this. We move right, we don't move left from the origin and so on. Graph the position function. Part B, graph the velocity function. When is the object stationary, not moving, staying still? When is the object moving to the right? When is the object moving to the left? I noticed that I'm missing part C, but part C is the velocity at 1, I believe. It's not really something big, but we're going to see the answers. I couldn't fit in this problem everything with the calculations. So as we go, you will know what I'm talking about. We're talking about a lot of different things. We're going to graph it. We're going to discuss the graph. I'm going to talk about when the object is not moving. I'm going to talk about when the object is going to move right, when the object is going to move left, when, what else? Determine the acceleration when the velocity is 0. We're going to talk about when the object is speeding or the speed is increasing. Position, velocity, and acceleration. This example is f of t equals t to the second minus 4t between 0 and 5. Here's a graph for part A. Since it's a second degree parabola that opens up because the leading coefficient is positive, it's going this way from 0 to 5. And if you notice on the graph, I have a green color and a red color. I graphed f prime. F prime is the first derivative, 2t minus 4. It's a straight line with y-intercept -4 and a slope of 2. Now at this location, we have a horizontal tangent. So f prime should be crossing the x-axis because f prime is 0, right there. On this portion, if you're walking on the graph, you have negative slopes of tangents. So your graph should be below the x-axis for the prime. Here, the tangents are giving you positive slopes, so you should be graphed above the x-axis. Here's another hint or comment about f prime line. We call it f prime sign. We call it f double prime sign. If you take f prime 2t minus 4 and make it equal to 0, you add 4 to both sides, then you divide by 2, you get 2. So these refer to f prime. F prime at 2 is 0. To the left of it, it's negative. The graph supports it. To the right, it's positive, and the graph supports it. But if you don't have the graph, you could just do it yourself. If it crosses the x-axis at 1, 0, which is when t equals 2, that means it went from below to above, or the other way around. It was above the x-axis and it went through the x-axis at 2, down below. But we see the graph, so you could test it by plugging numbers. Any number will do. For example, to the left of 2, I'm going to plug in 1. 2 times 1, 2. 2 minus 4, -2. That's the negative. On the right side, I could pick 3 or 4 or 5. For the convenience, I'm going to pick 5. 2 times 5, 10. 10 minus 4 is positive 6. So everything here should be positive. So the graph should be above the x-axis. That's one of the benefits for graphing a line for the signs of f prime. Also, as a hint, if f prime is negative on an interval, that means the graph originally, which is f of t, is decreasing. And if it's positive, the graph is increasing. In this case, we're looking at f of t, which is position, velocity, and acceleration. When f prime is positive, which is velocity, we say that the object is moving forward. We don't say the graph is increasing. If the first derivative, which is f prime, which is in our case velocity, negative, we say the object is moving to the left. Object is moving to the right. Object is moving to the left. Now here's another hint about f double prime. F double prime, if it's positive, like in this case, it's always positive. It doesn't change. We say that the graph is concave up. I think we could see that right here. This is called opens up, or formally we call it concave up. Pretty much I covered everything, but let me show you all the notes in steps. Part B, f prime is 0. Set it equal to 0, you get 2. That is when the object is not moving. Between 0 and 2, this portion, f prime is negative, which means the object is moving to the left. From 2 to 5, above 2, f prime is positive, the object is moving to the right. Part C was asking about what is the acceleration and the velocity at 1 after 1 second. So you have f prime, plug in 1, you get -2 feet per second. Find the derivative of this, which is always 2. F double prime at 1, it doesn't change from 2, it's 2 feet per second square. Part D, they're asking what's the acceleration when the velocity is 0. So what you do, take f prime, make it 0. That's the velocity, and that happens at 2. Take this 2 and plug it in. The second derivative, it doesn't change. So the acceleration at 2 when the velocity is 0 is 2 feet per second square. On the interval from 2 to 5, we have something new. F prime is positive, F double prime is positive. They're both positive. On the interval from 2 to 5, the velocity and the acceleration are both positive. That means the object is speeding up, or we say the object's speed is increasing. So you want to make a note out of this, and if it's too much, I'm going to summarize it for you as notes. F prime is positive, F double prime is positive, velocity is positive, acceleration is positive. That means the object speed is increasing. This time it's cubic. So my function is 2t to the third minus 21t to the second plus 60t. We're going from 0 to 6 this time. When I graphed it, I have 1 color, 2 colors, 3 colors, 4 colors. And I'm highlighting this point down here as 3.5. Increasing, decreasing all the way, then back increasing. This horizontal tangent, so we have 2 horizontal tangents, which means the derivative crosses the x-axis at 2 locations, at 2 and 5, just to support. You are increasing, you should be above the x-axis. You are decreasing, still decreasing, you are below the x-axis for those 2 pieces or 2 colors. Here you are going up, you should be above the x-axis. Now why I'm highlighting or pointing to 3.5, you'll see it in the notes. I'm just gonna give you overview, so when I read fast you'll know at least what's happening. From this point to the left, the graph is concave down. From this point to the right, the graph is concave up. So this point has a name. We call it inflection point. Sometimes we call it the weakest point of the graph. That's why I'm kind of pointing to the 3.5, alright? Alright. F prime is derivative of this, which is 6t to the second minus 42t plus 60. Take 6 out, I get this. Factor the inside part, set it equal to 0, I get 2 and 5, and they are within my domain, so I'm gonna mark them down. This line is for f prime, so f prime at 2 is 0, f prime at 5 is 0. Test it with numbers, positive, negative, positive, increasing, decreasing, increasing. The graph supports it, increasing, decreasing, increasing. And what makes it markers between increasing, decreasing are the zeros, which is 2 and 5. Now, the book or this problem is not designed for increasing and decreasing. They're saying moving right and left, so let's talk about that. For 0 to 2, that's this part, f prime is positive, so the object is moving to the right. When f prime is negative, that's between 2 and 5, the graph or the object is moving to the left. 5 to 6, positive, derivative, the object is moving to the right again. Part C, we need to find f prime at 1, 24, just plug in 1 right here or here. F double prime is finding derivative of this. 2 is going to go down, it's going to make it 12t, and this is minus 42, as you could see. This example is not constant like the last 2 examples, so now we're going to plug in 1. Plug in 1, you get minus 30 feet to the second square. Those units means we are referring to acceleration. Part D says what is the acceleration when the velocity is 0? Velocity is 0 when at 2 and at 5. Plug in 2 in the acceleration or the second derivative, plug in 2 in the 5 in the second derivative, we got minus 18 feet per second square, and we have positive 18 feet per second square. Part E. F double prime is right here, is positive. You set it equal to 0. Move the 42 to the other side, divide by 12, you get 42 over 12 or 7 over 2 or 3.5. And that is when the second derivative is 0. Test it to the right and left, you will find that it's positive to the right of it. That means concave up. And it's negative to the left of it. That means concave down. To summarize that, I'm gonna bring it right after this. So if f prime and f double prime are both positive, we are speeding up. But that happens when between 2 and 3.5. Between 2 and 3.5, they're both negative. This is negative. And between 2 and 3.5, f prime is negative. We're going down. Here it's negative, but f double prime is not negative after 3.5. It's positive because it's concave up. Here's the f double prime number line. Here's f prime. You could compare them back and forth and see if this makes sense. 3.5, f double prime is 0. To the right it's positive, concave up. To the left it's negative, concave down. Concave up, concave down. If you put this line on top of this line, kind of aligned, you will see positive, negative, positive. So we have here both negative on 2 and from 2 to 3.5. So that is where the object is speeding up. You could align it and double check. Here to the left it's negative, but let's double check to 0. Yeah, I have to align them to be careful. So let me summarize that and make it more as notes this time. But I'm adding more to this section, and it doesn't hurt because calculus is so much connected, and the more that you know, that's going to help you with the coming sections. Bonus number 1. F prime of x equal greater than 0. That means f of x is increasing. Now I'm not saying s prime, I'm saying f prime. F prime of x is negative. That means the graph is decreasing. Bonus number 3. If f prime is 0, f of x has a horizontal tangent. Bonus number 4. This is not in this section, but why not? F double prime is positive. That means the graph is concave up. See this sign? I usually use this sign to help my students memorize which one is concave up and which one is concave down. So if double prime is positive, we call it concave up. If double prime is negative, we call it concave down. I think it's not nice and it's not good to be negative. Negative is like a sad face. Positive is a happy face. Concave up, concave down. Hopefully that helps. Sometimes we do things like that to help memorize. Hopefully you like it. 2 more. Bonus number 6. F double prime, if it changes sign at x equals a, from positive to negative, from concave up to concave down, or the other way around, from concave down to concave up, at x equals a, we call a an inflection point. Bonus number 7. Object is speeding up if v of t and f t have the same sign. Object is slowing down. This was not covered in the examples. I could cover it, but those slides were kind of filled. If v of t and f t have opposite signs. You might not memorize this, but keep a note out of it for any problem that you might face later on. Object is speeding up if v and a have the same sign, and the object will be slowing down if v and a have opposite signs. Let's take an example. A dropped stone on earth. The height in feet of a stone dropped from a bridge 64 feet above a river at t equals 0 seconds is given by s of t equals minus 16 t to the second plus 64. Notice this is a parabola upside down because negative leading coefficient, and it makes sense. I'm going to support it with the graph. Find the velocity of the stone and its speed when it hits the ground, or the water, I mean. Because we're not throwing from a building to the ground, they're throwing it from a bridge to the water or the river. To find out when it hits the ground, of course, we're going to set s of t equals 0 because you are on the ground level, you are not lifted up. Basic algebra. Take this, set it equal to 0, move this to the side, divide both sides by negative 16, and get t squared equals 4. And you might say, how come it's not plus minus 2? Well, we're dealing with application. We're not going back in time. That's why. So t equals negative 2 is not part of the game right here. So t equals 2 is the time the stone hits the water. The velocity at t is v of t equals s prime, which is the first derivative of this guy. 2 comes down, makes this negative 32t, 64 will be 0. So minus 32t. So v of 2, the velocity at t equals 2, when the stone hits the water, is negative 64. The velocity of the stone and the speed when it hits the water. So we're done with the first part. To do the second part, the speed, we just take the absolute value because speed is never negative. Alright, let me support these ideas within a graph. You're throwing it from the bridge down to the water. It hits the water or the river surface after 2 seconds. You started from a height of 64 right here. This is your position function. When you're down here, s of t is 0, not 64. V of t will be the tangent, which is velocity, and the speed will be the absolute value. Another example. Suppose a stone is thrown vertically upward, now this time upward, not down, from the edge of a cliff on Earth with an initial velocity of 64 feet per second from a height of 32 feet above the ground. The height in feet of the stone above the ground t seconds after t is thrown is s of t equals negative 16t to the second plus 64t plus 32. This time I was able to fit everything in one page, and I'm reading it a little bit fast, but we're gonna see everything clear. Velocity in general after t seconds. This is the position. Just find the derivative, which is right there. We know how to find the derivative of this, and that's the answer. Negative 32t plus 64. B. When does the stone reach its highest point? What do you think? How do you find the highest point? Well, this is a parabola upside down. So it's kind of like goes up, then goes down. So how do you find the maximum point? Well, in algebra we call it vertex, and we do things of that nature. Here we have another technique. So if you go on the graph this way, I think one way to find this highest point is a horizontal tangent concept. So we need to find the first derivative and set it equal to 0. V of t, set it equal to 0. That's V of t. Minus 32t plus 64 equals 0. Move this to the side, divide by negative 32 after 2 seconds. Good to know. Part C. What is the height of the stone at the highest point? That means at t equals 2. Plug it in right there. 96 feet. When does the stone strike the ground? Well, the stone will hit the ground when s of t equals 0. So s t equals 0. Plug 0 here. Plug 0 here to the right and solve this algebraically. Kind of hard to factor it, so we ended up using the quadratic formula. I know this is not a good number to deal with, but sometimes in calculus we have this, not all the time. Most of the time we have numbers that we could handle even without calculator, but once in a while, as we know in life, numbers are not always just integers. We have decimals, we have negatives, we have fractions, so sometimes we have to deal with those. Notice that this one is not 2 plus minus because we are referring to time, and we started with t equals 0. If you do the approximation, it's 4.45 seconds. It will hit the ground after this much. With what velocity does the stone strike the ground? Okay, we know the time that's gonna hit the ground. We just plug it in the velocity, and the velocity is right here. You just plug in this 2 plus square root of 6, or plug in this for approximation 4.45 in v of t, which is this right here, or this right here, and we get negative 78.38 approximate feet per second. Part F. On what intervals is the speed increasing? The acceleration due to gravity is always negative. So the object is speeding up when the velocity is also negative. To the number line for the v or f prime, you will find that between 2 and 2 plus square root of 6, or roughly between 2 and 4.45. I kind of mentioned how the graph looks like this for this, but let me support. So the graph looks like this, up, then down. The object was, or the stone was thrown from a height of 32, reached the maximum height at t equals 2, got to the ground level after t equals 2 plus square root of 6. Gravity, downward journey during the interval 2 and 2 plus square root of 6. Velocity is negative. The tangents have negative slopes, and gravity is negative because you're going down. So that's when the object is speeding. That should do it for now, and I made it about close to 40 minutes. Not too bad. The other videos after this are short and they're gonna go quick. Thank you for watching. Thank you. Thank you for watching. If you like this video, subscribe and give it a like, and I'll see you in the next one. Thank you.